Download this code from codegive.com, link in the description below. Manchester encoding and differential Manchester encoding, a detailed tutorial. Manchester encoding and differential Manchester encoding are line coding techniques used in digital communication to transmit data over a physical medium. They are popular due to their self-clocking properties, meaning that the clock signal is embedded within the data signal, simplifying clock recovery at the receiver. This eliminates the need for a separate clock signal and improves synchronization, especially over long distances or noisy environments. This tutorial will cover 1. Introduction to line coding *, why we need it and the benefits of self-clocking codes. 2. Manchester encoding * how it works, encoding rules, advantages, disadvantages, and code examples. 3. Differential Manchester encoding * how it works, encoding rules, advantages, disadvantages, and code examples. 4. Comparison * Manchester versus differential Manchester. 5. Applications * where these encoding schemes are used. 6. Code examples * implementation in Python with explanations for encoding and decoding. 1. Introduction to line coding. Line coding is the process of converting digital data, bits 0 and 1, into electrical signals suitable for transmission over a physical medium, example copper wire, fiber optic cable, wireless channel. Without line coding, simply representing 0 as a low voltage and 1 as a high voltage can lead to problems. DC component * a long string of zeros or ones results in a DC, direct current, component in the signal. This can saturate transformers and cause signal distortion. Clock recovery * a long string of zeros or ones makes it difficult for the receiver to determine the bit boundaries, i.e., where one bit ends and the next begins. This is because the receiver needs to synchronize its clock with the transmitter's clock. Error detection * simple binary encoding offers limited error detection capabilities. Benefits of self-clocking codes. Self-clocking codes address these issues by embedding the clock signal within the data signal. This is achieved by ensuring that there is a transition, change in voltage level, within each bit period. This allows the receiver to reliably extract the clock signal from the received data, simplifying synchronization and improving data integrity. 2. Manchester encoding. Manchester encoding is a synchronous clock encoding technique that encodes each bit of data with a transition of voltage. How it works *. In Manchester encoding, each bit period is divided into two halves. The representation of a bit is determined by the transition that occurs in the middle of the bit period. Encoding rules * logic 0 * a transition from high to low voltage in the middle of the bit period. High-low. Logic 1 * a transition from low to high voltage in the middle of the bit period. Low-high. Visual representation *. Advantages *. Self-clocking * guarantees a transition in the middle of each bit period, enabling easy clock recovery. No DC component * the transitions ensure a balanced signal, reducing the DC component. Relatively simple * encoding and decoding are straightforward. Disadvantages higher bandwidth requirement * Manchester encoding effectively doubles the bandwidth required compared to simple binary encoding. For each bit of data, two signal transitions are needed. Overhead * introduces overhead due to the need for transitions. Code example, Python. Explanation *. Manchester _encode, data. This function iterates through each bit in the input data. If the bit is 0, it appends HL, high-low transition, to the encoded underscore signal. If the bit is 1, it appends LH, low-high transition, to the encoded underscore signal. The trailing comma is removed before returning the encoded signal. Asterisk Manchester underscore decode, encoded underscore signal. This function splits the encoded underscore signal into a list of symbols, HL, LH. It then iterates through each symbol and appends 0 to the decoded underscore data if the symbol is HL and 1 if the symbol is LH. Asterisk note asterisk this example uses HL and LH to represent the high-low and low-high transitions. In a real implementation, these would be represented by actual voltage levels or other physical signals. 3. Differential Manchester encoding. Differential Manchester encoding is another synchronous clock encoding technique that encodes data based on transitions rather than absolute voltage levels. This makes it less susceptible to polarity reversals in the transmission medium. How it works asterisk. In differential Manchester encoding, a transition always occurs at the middle of each bit period. The logic value is determined by the presence or absence of a transition at the beginning of the bit period. Encoding rules asterisk. Asterisk logic 0 asterisk a transition occurs at the beginning of the bit period, in addition to the mandatory transition in the middle. Asterisk logic 1 asterisk no transition occurs at the beginning of the bit period, only the mandatory transition in the middle. Visual representation asterisk. Assume the previous bit ended with a high-low transition. Key idea asterisk the encoding depends on the relative change in the signal, not the absolute level. Advantages asterisk. Asterisk self-clocking asterisk guarantees a transition in the middle of each bit period, enabling easy clock recovery. Asterisk no DC component asterisk the transitions ensure a balanced signal, reducing the DC component. Asterisk less susceptible to polarity reversals asterisk because the decoding is based on transitions, the signal is less affected by polarity inversions. Asterisk better error detection asterisk errors are more easily detectable because of the stricter transition rules. Disadvantages asterisk. Asterisk higher bandwidth requirement asterisk similar to Manchester encoding, it effectively doubles the bandwidth compared to simple binary encoding. Asterisk more complex implementation asterisk slightly more complex to implement than Manchester encoding due to the need to track the previous bit's ending level. Code example, Python. Explanation asterisk. Asterisk differential underscore Manchester underscore encode, data, initial underscore level. This function maintains the current underscore level, either H or L. For each bit. Asterisk if the bit is 0, transition at the beginning, it checks the current underscore level. If it's H, it adds LH to the encoded underscore signal and updates current underscore level to L. If it's L, it adds HL and updates current underscore level to H. Asterisk if the bit is 1, no transition at the beginning, it adds HL if the current underscore level is H or LH if the current underscore level is L, without changing current underscore level. This forces the midpoint transition but doesn't create a transition at the beginning. Asterisk differential underscore Manchester underscore decode, encoded underscore signal, initial underscore level. This function splits the encoded underscore signal into a list of symbols and iterates through each symbol. Asterisk it determines the next level based on the symbol, HL becomes L, LH becomes H. Asterisk it then compares the next level with the current level. If they are different it decodes it as a 0. Otherwise it decodes it as a 1. Asterisk important asterisk the initial underscore level is crucial for correct decoding. The decoder must know the initial level used by the encoder. 4. Comparison, Manchester versus differential Manchester. Feature Manchester encoding differential Manchester encoding. Encoding basis absolute voltage levels transitions. Polarity sensitivity susceptible to polarity reversals, less susceptible to polarity reversals. Complexity simpler, slightly more complex. Error detection less robust, more robust. Clock recovery good. Bandwidth requires higher bandwidth. 5. Applications. Ethernet, 10 base T Manchester encoding was used in the original 10 Mbps Ethernet standard. Token ring used in older token ring networks. RFID, radio frequency identification. Both Manchester and differential Manchester encoding are used in RFID systems for data communication between the reader and the tag. Magnetic recording used in some magnetic recording systems. 6. Summary. Manchester and differential Manchester encodings are valuable techniques for digital communication, especially in environments where clock recovery is essential and DC component issues need to be addressed. While they require higher bandwidth, their self-clocking properties and robustness against noise make them suitable for a variety of applications. The choice between Manchester and differential Manchester depends on the specific application requirements, particularly sensitivity to polarity reversals and the acceptable level of implementation complexity. Differential Manchester's robustness against polarity issues makes it preferred in many industrial and data acquisition scenarios where wiring may be unreliable.